Let's solve question 2 from the April 11th worksheet. We have this circuit. Initially, the switch is open. There's no charge on the capacitor, and there's no current flowing through the inductor. So at time 0, we close the switch, and then an instant after closing the switch, what is the current through the inductor? I labeled that I2 flowing through the inductor. So the current through the inductor just before we closed the switch was 0. It takes some time for the current through the inductor to change. So the current through the inductor immediately after we close the switch is also 0. Charge in the capacitor is also still 0 immediately after we close the switch. So let's find these three currents immediately after we close the switch. So I think I could write the loop rule as the battery EMF minus I1 R1 minus L di2 dt minus I2 R2 equals 0. That's for this loop, starting at the top of the battery, going around clockwise down through the inductor back to the bottom of the battery. And then I could also make a loop. I'm going to start here. So I'm going to go up through the resistor, up through the inductor, and then back down through the capacitor. And I'm going to call this plus Q, and I'm going to call this minus Q on the capacitor. So how you write the loop rule for a capacitor depends on which plate you label as positive. So because we're going up, this is going to be plus I2 R2 plus L d I2 dt minus Q over C minus I3 R3 equals 0. But we know that I2 equals 0 immediately after we close the switch. So at t equals 0 plus, we have I2 equals 0, and that actually implies that I3 equals I1. So in fact, I didn't use the loop rule equation I think I actually wanted to use. I really wanted to go from the top of the battery to the right through R1, and then across, and then down through the capacitor, and to the left through R3, and back to the bottom of the battery. So that's really the loop that I wanted, the outside loop, because both of these expressions involve the rate of change of I2, which I don't really want to think about yet. So in fact, if I just added these two equations, I would get the same result as I get by applying the loop rule to the outside here. So let's just apply the loop rule to the outside here. And I get the battery EMF minus I1 R1 minus Q over C minus I3 R3 equals 0. And then I3 is the same as I1, and Q over C equals 0 at this initial time. Now I have something I can work with. So this gives me that I3 equals I1 equals the battery EMF divided by R1 plus R3, since I3 equals R1, and we have I2 equals 0. Okay, I think that was interesting. This was actually an interesting wrong track. Now we want to know what is the induced EMF in the inductor this instant after the switch is closed. So that's just this term, L di2 dt. So we have EMF induced is L di2 dt. That equals the battery EMF minus I1 R1, and then in general it's also minus I2 R2, but I2 is 0 the instant after we close the switch. So this is my answer. It's the battery EMF minus I1 R2, which we just solved for here. So we worked out over here that I3 and I1 were both 37.5 milliamps, and I2 was 0, so then the induced EMF is this expression, which equals the battery EMF minus I1 R2, so then that works out to be 11.25 volts. Now we want to know, after the switch has been closed for a long time, what are the currents through the three resistors. So after the switch has been closed for a long time, the capacitor charge will be constant. It will have reached an asymptotic value. So if this charge is constant, then dq by dt is 0, and you can see that I3 equals dq by dt, so I3 will be 0. Meanwhile, I2 will be some constant value through the inductor, and therefore di2 by dt will be 0, so the induced EMF in the inductor will be 0. So now, after the switch has been closed a long time, this current is 0, and this current is constant. So if I3 is 0, then I2 equals I1, and then we can use this equation That means I2 equals I1 is the battery voltage divided by R1 plus R2. Then, after the switch has been closed a long time, what is the charge on the capacitor? So we can use this second loop rule equation. Actually, there are only two non-zero terms here, so this tells us that Q over C equals I to R2. That gives us Q equals I to R2C, which is 50 milliamps times 200 ohms times 600 microfarads. So this is 6 millicoulombs, so 6,000 microcoulombs. Final charge on the capacitor. I think we know in this problem that the charge on the capacitor looks like this. So it starts out at 0, and then after a long time it reaches some asymptotic value. And then its rate of change is the current, I3. So it starts out at some maximum value and decreases. Then the current I2 through the inductor starts out at 0 and then eventually reaches some asymptotic value. And then the induced EMF is the inductance L times the rate of change of I2. So it starts out at some maximum value and then decreases to 0. This time constant is some resistance times this capacitor value. I think it might take us a moment to figure out exactly what resistance that is. And then this time constant is L over R, this inductance divided by some combination of resistors. And I think it would again take us a moment, maybe we have to even write down the differential equation to figure out exactly which combination of resistors that is.